Is it a full screen? Okay, so let's start. So this is fifth week. We are discussing on the topic characterization of polymers, elastomers, and composite, already taught by Professor Santanu Chattopadhyay. And here myself, Somadesh Ghosh from IIT Roorkee. So I'm taking the doubt clearing classes to complete my TA work. So today we will not discuss any new topic. So last week what we have discussed, we'll recapitulate it basically. So uh, I think you have remembered that we are discussing about some electromagnetic radiation and then spectroscopy, different spectroscopy technique. And we have also discussed basically two spectroscopic techniques. One is UV visible and another one is FTR spectroscopy. So we'll discuss today in more detail about UV and FTR, and also we'll observe some real uh, FTR or UV data of organic molecules. So here the table is signifying uh, different spectroscopic techniques and the principle based on which the techniques are implemented, and also different electromagnetic radiation those are used for those spectroscopic techniques. So for UVs, it is obviously UVs radiation, and the principle is Lambert-Beer's law basically. Based on this law, the UVs analysis is going on. FTR is based on the functional group analysis to determine different functional group present on any substrate or any material. And the radiation that is used for FTR spectroscopy is IR or microwave radiation. For Raman, this is also a functional group analysis technique, and it is a quantitative analysis technique. For Raman, we need UV or visible also, and basically laser is used in case of Raman spectroscopy. It's not a spectrum of light, it is a single wavelength light that is required for Raman. And for NMR, we need radio wave, and this is a very sophisticated technique. From NMR, there are different kind of NMR actually. One is proton NMR and 13C NMR or fluorine NMR, and this is used to determine any structure of any molecule. From NMR, you can 100% you can assure that okay, my structure is this, but from FTR you cannot confirm what is the structure. And for XPS we need X-ray, and that is required to confirm different element or basically presence of different element in a composite. And you can also analysis quantitatively that how much percentage of different elements present in your sample. In XRD, that is nothing but to determine the 3D structure of any molecule. Now, how actually the uh, probing of electron in different spectroscopic technique works. So in case of X-ray, the responsible electron is the inner electron that is closer to the nucleus of an atom. In case of UVVs, since it is a transition spectroscopy, basically electron transition happen in case of UVVs analysis. So outer electrons are responsible for this. In case of FTIR or IR, it is basically the molecular vibration, and in case of microwave, it is molecular rotation. How I have already discussed in last week that how electromagnetic spectrum originate from orientation of electron. So just to summarize it, so the change of orientation, it will generate dipole moment during rotation, and then based on that the molecule will, or the bond basically will resonate with electromagnetic radiation. So during rotation, the dipole moment will change. So obviously the molecule should have a permanent dipole moment, or it must be polar type of molecule. Then only during rotation the dipole moment will change. So obviously homonuclear diatomic molecule will be IR inactive. If you put it, or if you radiate it with IR radiation, there will be no changes will be happen inside the molecule. But if it is a heteronuclear diatomic molecule, or it is a polar molecule, if you irradiate it with IR radiation, it will respond. So you must be careful about the polarity of your polar nature of the molecule, whether it will be IR active or IR inactive. And how you can assure that whether the molecule will be polar or non-polar? Obviously, by looking its structure, you can say, okay, it will be polar, or if it is a homonuclear, so it must be non-polar type. Now, in case of UV phase, it is basically absorption spectroscopy, and that's why it is also a quantitative analysis. So what is happening here? You put your sample in a cuvette, irradiate it with UV light, and obviously it will absorb the light. The rest transmitted light, from here it is the transmitted light, and you will check that how much absorption is taking place. And what is happening? The electron is transitioning from its ground state to excited state. This is the basic fundamental thing. Now, the law behind CVV is, that is Beer-Lambert's law. So one is talking about the concentration of your sample, and another one is talking about the path length, that how much, what is the width of your cube head, and based on that you will plot absorption versus concentration. So to check if someone is working on any ion absorption type of research work, and someone is developing some membrane and how much it can absorb any ions. Let's assume that if somebody is try to absorb arsenic from water solution, so how much absorption is taking place, you can determine that from the UV spectroscopy quantitatively. So what Beer-Lambert's law says that obviously it is two parameter, one is the concentration and path length, and it is a additive type property. A has absorption has no limitation with respect to the path length. If the path length is higher, so obviously absorption will be also higher. Now, if the concentration is very much high, so it's better to use low path length or smaller short path length. And if the path length is high, your sample concentration should be low. And it is also additive type, uh, additive nature. So if you have a 3 or 4 different uh, sample, and the proportion is different, so based on the concentration the absorption also will be different. Now the total absorption will be the summation of all the coefficient. Sorry. The quantitative picture is, absorption usually becomes nonlinear if the concentration is very much high. If it is greater than 0.1 molar, so the absorbance will not be linear type. The second is above concentration 0.1 molar. Why it is happening? Because if the concentration is too much high, so the distance between two ions will be very much low. And when the distance is very much low, it will affect the charge distribution surrounding the ions. And when it is disturbing the charge distribution, obviously the electron transition will be disturbed. And when it is the electron transition is disturbed, so the absorptions of the UV light will be disturbed. So that's why if the concentration is too much high, it may not be the linear. And second, another thing is if chemical reactions occur. For example, with time, if your sample or the active material is reacting with your solvent, so then of course the electron transition will be hampered, and then also you will not get a linear type of curve if you plot the concentration versus absorbance. Or if it is dissociated with time, then also it will create problem. And sometimes if your molecules is fluorescence positive or phosphorescence, it has phosphorescence type of property. So there is two term, one is fluorescence and there is phosphorescence. That happens based on the stability of the single electron. So if material is fluorescence active or it is showing the phosphorescence property, then also you may not get the linear type of curve. Now why it is happening? Because it will ultimately now the phosphorescence and fluorescence is also electron transition. So there is a different chemistry. From singlet there are different terms, singlet, triplet, etc. So that's why material sometimes it is active or it will show fluorescence and phosphorescence based on the electronic structure. So if it is showing this property, so in case of UV, it may hamper the analysis. If you have any doubt, you may ask me. This is a little bit uh, chemistry oriented basically. So if you are not getting it, so please stop me and ask. Now this is very important. So yesterday I have also discussed it. Now I think you have a little bit idea after the previous discussion. Now today we will again elaborate it that what is happening during the UV analysis. So as I already told you that this is electronic transition. So there are different state. If you plot in an energy diagram, so this is sigma bonding, this is pi bonding, this is non-bonding, this is pi star and sigma star. What this sigma star pi star mean? This is basically the molecular orbital. When two atoms are forming a molecule, how the valence bond of the atom are participating to form a molecular orbital, and after that how the energy based on the energy how it will be oriented. So the least or the most stable one is the sigma bonding, then pi bonding. So always bonding orbital have least energy because they are much more stable. Then the non-bonding where the lone pair is uh, present, and then pi star antibonding, and at last the sigma star antibonding. So there are different possibility of electronic transition. So first is sigma to sigma star, but it is difficult to get in the UV because of this large energy gap. So energy is required much higher, and that may not be equivalent to the UV. So that's why it is difficult to get the absorbance peak in case of UV corresponding to the electronic transition from sigma to sigma star. The next is sigma to pi star. So it is little bit less and it is comparable or it may resonate with the UV light energy. The third one is pi to sigma star or pi to pi star. And the last one is n to pi star or n to sigma star. Usually for any organic molecule, most of the time we will get pi to pi star or sigma to pi star or pi to sigma star or n to pi star. These four are the most possible outcome of uh, in UV analysis. The rest are because of the higher energy gap, it is difficult to get in case of UV. Now, what are the different molecules? First of all, you should look at the structure whether there is a presence of heteroatom or is there any lone pair electron? For example, if there is oxygen or nitrogen, so there must be lone pair, and they must show some absorbance peak in case of UV. So if the amine group or ketone group or aldehyde are present in your substrate or in your sample, it will show some electronic transition, and it will show the absorption property in if you perform the UV analysis. Is it clear? Okay. So here there's the this it is showing the corresponding energy and corresponding electron transition. So I have already told you that because of the higher energy, that is sigma to sigma star, that actually equivalent to the less than lambda equal to 150 nanometer. So that's why it is difficult to observe in molecular UV spectroscopy. Now other two possibilities, n to sigma star and pi to sigma star. So those transitions are coming under the 150 to 250 nanometer region. So you can see if there is a peak around these wavelength, so there are in either n to sigma star or pi to sigma star. The next is n to pi star or pi to pi star. That is the most common one, and the corresponding energy equivalent to lambda max is 200 to 600 nanometer. So what are the different shift possible in case of UV? So there are basically four shift. One is bathochromic shift or red shift. That means when your sample A is showing a absorbance around 200 nanometer, and after adding an additive, if the peak is shifted towards larger wavelength, that is bathochromic shift or red shift, and if it is shifted towards the low wavelength light or blue light, that is called the hypsochromic. So these are the change in the wavelength or shifting in x-axis. The another two term is hyperchromic or hyperchromic, that based on the intensity. If the intensity is higher, that is hyperchromic, and if the intensity get reduced, that is hyperchromic. So four different terms are usually used in this UV. If you are modifying your sample and if the peak intensity or peak position is changed, then based on change or based on shifting in different direction, the shift will be called as bathochromic or hypsochromic, or if intensity changed, then it will be called as hyperchromic or hyperchromic. Now here is the real example. So this molecule, it has two cyclohexane ring, one C double bond C, one pi bond between two carbon atom, and also there is presence of a aldehyde group, a ketone group. Now what are the different transition can take place? Now this molecule has all the orbital, all the molecular orbital like sigma, pi, and also because of the presence of oxygen, it has also non-bonding orbital because oxygen has lone pair. So what are the different transition can take place? As we discussed, the most probable one is the sigma to pi star or pi to pi star, sorry, say n to pi star or pi to pi star. Now how the transition from the, if you are getting this type of peak after performing the UV, now which peak is corresponding to which electronic transition? How you can designate that this peak is corresponding to n to pi star and this peak is corresponding to pi to pi star? If you understand the last slide, you can explain. If somebody responds, I will be happy that why this is n to pi star and why this is pi to pi star. Anybody please? Okay, so that's why you are saying that pi to pi star should come at uh, lower wavelength, because this is lower wavelength compared to n to pi star, right? Yes, because that is the high energy gap, so it is. Yes, yes, yes. So there are two different pi. One is the carbon oxygen and there is carbon and carbon. So yes, oxygen atom. That is coming from the oxygen and carbon. So from C double bond O, you are getting N to pi star. And C double bond C, you are getting pi to pi star. Now you may ask that why I am not getting pi to pi star of C double bond O. The reason is when there is a heteroatom. So if you little bit know about the molecular orbital theory, that the energy gap of pi to pi star in C double bond O, or the energy gap of between pi to pi star in C double bond C is different because of the difference in electronegativity. That's why in case of this bond, that is C double bond oxygen, the N to pi star is more feasible compared to pi to pi star. But in case of C double bond C, as there is no, first of all, there is no lone pair on any carbon, so there is only possibility of getting pi to pi star. And here the pi star transition is little bit less chance to get in UV because of N to pi star is much more prominent. The next is a simple molecule, that is, yes, yes, sure. Huh. Yes, 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 yes. Huh. No, but if you see the energy diagram, see N to pi star is much more less energy gap compared to N to sigma star. Yes, that N to sigma star and N to pi star, you see that energy gap in case of N to pi star is much more lower and it is much more comparable with the UV light. N sigma star. Yes, yes. So usually the most probable chance N to pi star, pi to pi star, N to pi star, pi to pi star, and N to sigma star. But that also depends on another different like the molecule structure also, because sometimes if there is a higher conjugation length, then it may seem that N to pi star energy gap is reduced somehow, and if it is interacting with hydrogen bonding or another ionic interaction, based on that sometimes you may also get N to sigma star. Only that you need to check that how it will deviate from the original molecule. For example, in case of A, if there is single molecule and if there is a mixture of two, and in that case maybe A and B are interacting. So when there are interaction, so there will be change in the energy gap also. So then obviously your number of peaks may also change. In that way, actually we are confirming what is happening. For example, if I am first taking a single molecule, let's say this one, and then I am hydrolyzing it. So how it is changing, there will be difference in the UV spectroscopy data. So if that lone pair If this lone pair is engaged with hydrogen bond, so it will be difficult to get the N2 pi star, because in that case now lone pair electron is bonded or interacting with another atom or another molecule or solvent also. Now this is another example of a very simple molecule, that is monomer of natural rubber, cis-isoprene. So there is only sigma and pi bond. So obviously there is also two antibonding orbital, that is sigma star and pi star. So you see only one peak is showing here. That is because of pi to pi star transition, and this is corresponding to 222 nanometer. So there are two bonding orbital, molecular orbital, sigma and pi, two non-bonding molecular orbital, sigma star and pi star. Now since pi to pi star is less energy gap, so we are getting only pi to pi star peak in UV spectroscopy. Is it clear? Okay. Yes, there is no null pair electron because carbon has no null pair electron. So you will not get any sigma N2 pi star. But if you halogenated it, or if you make it a saturated, then you will not get any peak, because in that case there will be no pi or pi star if it is all are saturated. That means there will be no any double bond. So it will not show any positive data in UV spectroscopy. Here is interesting one, that how your functional group, if I am changing the functional group, how it will impact the peak position. So for example, these are the all pi to pi star base value. Base value means the peak position. This is the all are peak position of pi to pi star transition. Now if you see, this is a cyclohexane ring and there is one double bond, and this is conjugated. So this is 215. If it is 5-member ring, this is 202. If this is uh, a C double bond O and it is also conjugated another C double bond C, but this is not C double bond C, now it is C double bond O. So it is little bit increased to 227. Now if there is a presence of another methyl group, now it is again increased to 239. So these are coming from the Woodward calculation. So how from the base value, if you functionalizing or if you are doing some modification, how the pi to pi star base value will change. Now this molecule is the enone. Basically this is called enone because there is ene and also ketone. That's why these are usually in general it is called enone molecule. If this is substitution X is hydrogen, it is 207. Okay, 207 of what? The pi to pi star. Now when if you are substituting X with R means any methyl or alkyl group. So now it is increased to 215. Now why it is happening? Because if it is R, so there will be a inductive plus I effect towards this carbon. When there is an inductive effect, the energy level will be changed. So when there will be a plus I effect or it is donating electron density towards this, so there will be a higher wavelength. That means now the gap is again reduced. The bonding and non-bonding gap is again reduced because you are increasing the energy density towards the bonding orbital. From here you will get better. So let's say this is pi to pi star is 215. Okay. Now if you are increasing the energy electron density in pi bonding, so obviously it will be little bit increased. Okay. Now when it is increased, so before pi to pi star the gap, now after this increment the pi to pi star gap will be reduced. Clear or not? Is it clear that if when I am substituting a this hydrogen with methyl, okay, now I am substituting this hydrogen with a methyl group. That means now methyl group has a plus I effect. What is plus I effect? It has a tendency to donate electron. Okay. Now, if it has a tendency to donate electron, it will obviously increase little bit energy electron density in bonding orbital. Now, when energy density will be increased, electron density, so the modified pi to pi star gap will be reduced. That means the peak position will be shifted to higher wavelength. So you will get the absorbance peak at a higher wavelength when the electron density will increase in the bonding orbiter. That's why from hydrogen to any alkyl group, you will get 2072 to 115. That means 8 nanometer will be shifted towards the red red light direction. Is it clear or not? Because this is important. Okay. First, you see that the most possible transition is pi to pi star or n to pi star. Let them aside. Just look at n to pi star and pi to pi star. Okay. Because electron transition will happen only from bonding to anti-bonding or non-bonding to anti-bonding. Because in anti-bonding there is no electron, na? Please keep silent, respond. Because there is a chance only transition from bonding to anti-bonding or non-bonding to anti-bonding. Because there is no electron in anti-bonding orbital. Now, if I am substituting this X, previously it was only hydrogen. So pi to pi star transition is taking place at 207. Now, when I am substituting this X with a methyl group, now methyl group or any alkyl group has a plus I effect. What does it mean, plus I effect? It has tendency to donate electron density towards this carbon. This carbon means these pi, these electron density in pi bonding orbital will be increased little bit through plus I effect. Now, when electron density is increased, now the energy of this pi bonding will be little bit increased. Now, when it is increased, so obviously the pi to pi star gap will be reduced, na? If this position is shifted towards the upper direction, so the gap between this pi star, now pi is not here, now pi is coming here. So it will be reduced, pi to pi star gap. That's why you will get the absorbance peak at higher wavelength. Because wavelength is high, that means the energy requirement is low. Why this is happening? Because the position of the pi bond is little bit increased towards higher energy because of the plaza effect of the alkyl group. Is it clear now? If somebody has doubt, I will repeat again. Now, next example is also uh, should I once again I will discuss. Okay, okay. Let's now first I am substituting that hydrogen with the alkyl group, and this is shifted to 215. Okay. Now, if I am substituting this X with a hydroxyl, now it is reduced from 207 to 193. Now, why it is happening? So reverse is happening, na? If I am substituting hydrogen with a alkyl group, it is increased. But if I am substituting this with a hydroxyl, it is reduced. That is because of the change in the electron density or the energy level of the pi bond. Because in case of OH, as oxygen has a electronegative effect, so it will reduce the electron density of the pi bond. So when there is a plus I effect, that pi bond will be shifted towards the higher energy direction. Let's say here it is coming here if I am substituting with a alkyl group. Now when I am substituting that hydrogen with a hydroxyl, in that case the pi will be coming towards in that direction. It will be again reduced, the energy level will be in a lower direction, because OH has a electronegative effect. It has not plus I, it has minus I. So it will stabilize the pi bond by bonding much more. So then the gap will be increased, and that's why you are getting 193. That's why you are getting 193. Is it clear? Why this is increased? Because of the increment of the electron density in the pi bonding orbital, and it is shifting the pi to pi star in a, the gap between pi to pi star is reduced because of the plus I effect of the alkyl group. Now when it is a electronegative group, so pi to pi star is increased. One case it is decreased, and the next case it is increased because of the electronegativity of the substituent. In case of R, it is plus I. In case of OH, it is minus I. Is it clear? Ha. Please. Yes. Ha. Yes. CS3. Yes. In that case, this pi bonding orbital will be shifted in this direction, upward direction. Because why it, you should clear, you have a clear idea why it is shifted to upward direction. Because of the plus I, the electron density in the bonding orbital is increasing. That's why it will be shifted towards the upper direction. Now, why, you may ask me that why, sir, electron density increasing, why it is shifting to upper energy level? Because usually in bonding or anti-bonding, there is the maximum electron can occupy is 2 electron, right? 2 electron. Now, because of the plus I, so basically you are increasing the electron density from 2 to 3 type. It will not 3, but you may say in that way. It's not 2, it is more than 2. So that's why it is shifting towards the upper direction when it is plus I. But if it is minus I, when it is hydroxyl, it has minus I effect, because oxygen is much more electronegative. It will attract the electron density towards its nucleus. So in that case, that pi bonding orbital will be shifting in lower direction because of the minus I effect. So affinity, substituent, affinity of the substituent, because based on the affinity, the electron density will be changed. And when the electron density will be changed, the energy level of that orbital will change. So in case of plus I, it will be towards higher direction. In case of minus, it will be in the lower direction. So when it is again lowering, so ultimately the pi to pi star gap will be increased. Now when it is increased, so it will be blue shift. That's why you are getting from 207 to 193, because it is wavelength, na? So lower wavelength means higher energy it's required. Now is it clear? Okay. So this is the main thing in the UPVs. So whenever you are performing the UPVs, when for example if somebody is working on any membrane type material or functionalizing something, so how the electron density or electronic environment, for example if someone is substituting this X, so how the peak position will change, he will or she will get the idea from the UV and confirm it that yes, the functionalization or modification is happening. So next is the, or if you have any doubt in UV, I will discuss, or I should go for the IR. It is clear, na? Yes, sir. OR, OR. This OR means is also in case of OH or it is OCH3. So actually it may not be 193, it may be 194 or 195. But ultimately it will be reduced because of the presence of oxygen related group. Because compared to OH, OR has a little bit low minus I as compared to OH. If you compare OH or OR, so OR has a little bit less minus R compared to OH, but obviously it has a much more minus I than the hydrogen or alkyl. So now infrared, we have also discussed infrared. So it is basically deals with the infrared radiation and the interaction of higher radiation with the matter. So from the FTR spectroscopy, we are analyzing the presence of different functional group by interacting the material with the IR or infrared radiation. Now, most commonly the spectrum is obtained by measuring the absorption, or it may be the emission also. So only the difference if you plot the absorptions versus wave number, and if you plot the emission versus wave number, the direction of the peak will be just reverse. The position will be same, but direction will be reverse. Now what is the model? That is the simple harmonic oscillator model. So if you assume any molecule, for example, there are two atoms, one has the m1 mass m1 and another is m2, and those are bonded by a spring, but that is massless spring. Now from the Hooke's law, that F force constant is minus F into delta R. F is the force constant and this is the F is the attraction force and delta R is the distance between the two atoms. So this is the model to explain the bond of any two molecule, of any two atom. Now the vibration energy from the SHO model is equivalent to half k delta R square, and that is again equals to 2 pi square mu into mu OSC, that is the frequency of the oscillator, and delta R square. Now mu is the reduced mass, that is the m1 m2 divided by m1 plus m2, and if you do the solution of this equation, you will get the frequency is 1 by twice by root over f by mu. This is the basically the oscillation frequency or the frequency of that vibration of the bond. So this is the bond vibration frequency. From through SHO model, you are deriving what is the vibration frequency of a particular bond. Now that frequency is related with the bond constant or force constant F and also the reduced mass of that particular bond between two atoms. Now from here you will get the idea that how the peak in FTR will change if I am changing the bond strength or the atom. For example, if this is a triple bond, so F will be higher obviously, because C triple bond C has a higher bond strength compared to C double bond C or C single bond C. If you change this carbon with nitrogen, then also, because then the mu will be changed. So either by mass of the atom or the strength of the particular bond, these are the primarily two parameters that will actually control the vibration frequency of any bond, and from there you will get different peak position. So what are the what is the criteria to be IR active? So first of all, the molecule must be polar, and then the change during the bond vibration, the dipole moment will change, and higher will be the polarity, the intensity of the IR peak will be higher. Now there are different modes for sample preparation before doing the FTR analysis. There may be transmission type, it may be reflectance type, that is reflective surface is needed, it may be scattering, that is called drift, that is diffuse reflectance infrared spectroscopy by Fourier transform. So this is the how the drift model works, and this is the ATR mode. that is attenuated total reflectance. So this is the most simplest one. You just put your sample and you will get the data. Or if it is a liquid type, then you have to prepare a KBR palette. Then you should put that KBR palette in this position and you will get the data. Now, what is Fourier transform? It is basically nothing but a mathematical equation. So you are getting this interferogram from the FTR, and by doing that mathematical transformation, you will get this type of data. So from if you have done the FTR analysis, so we are used to get the data like this. So these are the different peak position. So you are plotting the percent of transmitters versus wave number, and you will designate what are the different functional group by observing the peak position. Now in case of ATR, this is the equation where NSP and NP are the ratio of the refractive index of the sample versus the support. Usually for the support, sometimes diamond is used or zinc selenide also used. So what you need to do here, you just put your sample on the surface of the or the on the sample place. So it may be zinc selenide or diamond, and you will get the data. Now what are the advantage? So it is very easy to clean. After getting the data, you should clean it with any solvent. So usually people used to take IPA, isopropyl alcohol, to clean the surface of that zinc selenide or diamond. And you also the main advantage is you should not prepare any sample. Like if someone is doing the FTR in KBR, you have to first prepare a KBR palette. But in case of PTR, you don't need to prepare a sample. You just, whether it is liquid or powder or gel, you just put your sample and you will get the data. And there is non-corrosive liquids are not used. Soft powder, but it should not be very much hard. That is also ATR. You can also get the data from the ATR. Now this is the real example that how the atoms, what I have discussed from the simple harmonic oscillator model, that either bond strength or the reduced mass will change the peak position. From here you will get the data. So first of all, this blue color peak is a amine containing molecule. There is a presence of NH2. Okay. The next one, this red one, is some aldehyde containing molecule. Okay. Now when you are reacting the aldehyde and amine, you know that Schiff-base reaction is happening. So by reacting aldehyde with the amine, there will be a release of water molecule, and you will get imine bond, that is C double bond N. Now C. So there are these NH bond usually observed around 3500 or 3400 centimeter inverse. Okay. And aldehyde, the corresponding the characteristic peaks is to observe at 1700, that is C double bond O stretching. Okay. This is C double bond O stretching. This is C double bond C, that is coming around 1620 centimeter inverse, and the CsP3 hybridized age or CsP2 hybridized age is coming at 3000 centimeter inverse. Now when you are reacting aldehyde with amine, now CH double bond O, now this is converting to C double bond N, because the aldehyde is reacting with the NH2, there is a release of H2O, there will be C double bond N. Now you see, when it was oxygen, it was around 1700 centimeter inverse. Now it is substituted by nitrogen. It is coming at 1626 centimeter inverse. So it is clearly visible that by changing the atom, the peak position, how it is shifting. Now oxygen has higher mass compared to nitrogen, because molecular weight is 14 and it has 16. So since the reduced mass, that is in the denominator, so if it is higher mass, so it is observed at higher wave number. When it is lower, it is observed at lower wave number. And another thing, that is the bond strength in between C double bond O, C double bond O. In C double bond O has the higher bond strength. That's why it is coming at 1700. In case of C double bond N, it is coming at 1626. And from here, another observation is where the NH stretching was coming. Now you see, it is becoming broad. There is no sharp peak because NH2 is reacted with the aldehyde. That's why you are not getting a sharp NH peak. It is coming because of the, it may be in the presence of hydroxyl, or that hydroxyl is hydrogen bonded. Sometimes that's why you are getting broad type of peak, but there is no sharp peak what was observed when it was only amine. Is it clear that how the bond strength and reduced mass affect the peak position, and how you can confirm from the FTR that whether the reaction is happened or not? You can confirm clearly from the FTR. And you see, there is no peak observed at cell double bond O. In case of green, there is no peak around 1700. That means almost all aldehydes are reacted with the amine, and also there is no sharp peak around 3400 because all amines are reacted with the aldehyde. So from here you can uh, guess, or you can say, okay, the reaction is successful. But yes, it is also true, from the FTR you cannot conclude until and unless you are performing the NMR, because NMR is much more authentic compared to FTR. So after FTR, you have an idea, yes, the reaction is happening. It seems like that reaction is successful. Then you should go for the NMR. From there, it will be, you can be assured that yes, the reaction is successful. Yes. um, yes. Okay. Yes. Now, actually, what you should do if you are performing ATR, so first of all, you should take the baseline data without putting your sample. If moisture is there, it will become. When you are taking the baseline data, if there is a moisture, so it will come in baseline also. Now, when after taking the baseline data, you should put your sample, and then you should subtract the baseline data from the sample data. Then only you will get the ultimate or main data from your sample only. There will be no any error. And in case of KBR also, there is a possibility of moisture absorption, because usually KBR kept in 40, 60 or 70 degree centigrade oven. And when you are taking KBR from high temperature, in that time it can absorb moisture. So again, during KBR you have to first take the KBR data and then mix your sample with the KBR and prepare another pellet. Then take the data from the sample mixed KBR pellet, and again you have to subtract the KBR data from your sample data. In both cases, you first have to take the baseline data and then you subtract it from the sample data, and then only you will get the only sample data. But my suggestion is, if your sample is very much dark color, it will be difficult to get data from the ATR, because that works on the reflectance mode. So if say someone has a very dark color or black color sample, so you may observe that the peak intensity is much low. So you should go for the KVR mode. Otherwise, ATR is okay. If it is transparent or white type of or very light color compound, you can also take data from ATR. But it is very dark color, then it is better to take KVR mode data. But if you are asking about the moisture sensitivity, so there is a chance in both cases, both in ATR and KVR, that impact will be remain same. Okay. So this is another example of a silicon rubber. So there is a silicon oxygen bond that is coming at 10 around 1020 centimeter inverse, and the CH double bond CH2 that is coming here, that is also a intense peak, and Si carbon bond that is coming around 800 centimeter inverse. So usually in case of silicons, there are these are the characteristic peaks: silicon oxygen, silicon carbon, and carbon carbon. So this is the C double bond C peak. Here is the CsP2C. So there are different, actually you know that there are many functional groups, there are many stretching vibration mode. So you need to first know the what is the base value, and then if the substituents are changing, how the peak position will change. So basically you need to understand that how the electronic density or electron environment is changing when you are functionalizing or you are modifying something. Looking into the change in the electron density, you can expect that how the peak position will change. So this is another. Yes, yes, yes. This one, na? Yes. So actually, what happened? Sometimes there is also one term that is called vibronic coupling. So in that case, the peaks between splitted. That's why you may get also this type of splitting. So this is single peak, now it is splitting. It is called the vibronic coupling, or some that happens because of the electronic environment, and also because it is a rubber type material, so there is a very high entanglement of polymeric chain. So in that case, the electron density, it's not like a single molecule. So that is why this type of different interaction or coupling takes place. So it's usually ideally that what should come at a specific wave number for any specific bond. Now it is not coming in exactly that single type of peak. Because of that, those are because of different coupling. That's why you are getting a splitted type of peak. That may be the presence of that may be the CH3. That is it is not 3000, it may be 200 2900. That is because of the CsP3 hydrogen, because there is also CH3 group, na. So CsP3 hydrogen is coming usually around 200 2800 centimeter inverse. So that's why you are getting a sulfuric at higher number. And also it may be the merge. Actually it is not the exact data. There is also CsP2H, so sometimes it may be merged. In that case, it may comes around 2900 to 2000 3000 centimeter inverse. But there is also CH double bond CH2. So usually carbon hydrogen peaks appeared uh, for if it is saturated, it will come around 2800. If it is CsP2, then it will come around 2880 or 2900. If it is CsP, then it will come around 3000 or 3100, because the bond strength is changing. This is PVC type material. So you see, when there is also splitting here. That is because of the different coupling, and it happens when there is a heteronuclear bond, CCl. In there was Si, silicon and carbon. Here it is CCl. Now what are the other corresponding characteristic peak? One small peak is coming at 1720. It may be because of some additives or plasticizer. There is also a peak, that is CH2. Uh, it is not stretching, it is CH2 vibration, that is 1430 centimeter inverse, and this peak that is coming from the carbon hydrogen bond. So this is NBr PVC self crosslink blend. So there is also CCl and C triple bond N, if it is NBr nitrile. So it is coming around, it should come around 2000. Maybe this, maybe here it should come a peak because of the nitrile group. C triple bond N usually comes around 2100 or 2200 centimeter inverse. Now, when you are analyzing a composite, for example, it is a mix of two different or three different rubber. So sometimes from FTR it is difficult. That's because the intensity sometimes too much low, so it will not be clearly visible from the FTR data. Though it is present, but it may not be visible. And also for polymeric material, it is difficult to get exact the peak or very clear peak. The next is the butadiene rubber. Now, based on different structure, the how equation will change. For example, if it is a trans 1,4, so you are taking 1,4 butadiene and then you are polymerizing it. So there are different possibility. First, there may be some portion that is trans 1,4. There may be few monomer unit. Those are bonded with those are bonded like cis 1,4. There may be chance of 1,2 addition and also 3,4 addition. Now for Br, the characteristic peak, that is 1625, 1643 and 1666 for vinyl, cis and trans. So these are the C double bond C peak, carbon double bond carbon. Now when it is a vinyl, the peak C double bond C will be appeared at 1625. If it is cis, it will come around 1643. If it is trans, it will come around 1666. Now you may ask, you should understand why this peak shifting is happening. Because of the change in the electronic environment. That is the main reason. Because of the change in the electronic environment, the bond strength will be changed, and also the interaction will be changed, and based on interaction the electron density will be changed, and obviously the bond vibration frequency will change. So by looking at the structure, you should focus that how electron density is changing, and based on that what are the different interaction possible for a specific molecule. And other characteristic peak, that is CH working, that is here is also three different position, 967, 910 and 740 to 738 for trans vinyl and cis. Because of this structural difference, there is a changes in the bond vibration. And for styrene, you will get a characteristic peak, a very intense peak around 700 centimeter inverse. That is because of the carbon hydrogen of benzene ring. For any SBr type of material, for any SBr type of material, you will get a very characteristic peak around 700 centimeter inverse if you do the FTR. That is because of the styrenic hydrogen. Okay. So today we have summarized what we have discussed last week. today FTR and UV, and we have discussed with the real example also. Now, before going to the question answer, I should ask that if you have any doubt, uh, I will talk about that. Otherwise, I will go to the question answer. From FTR and UV, if you have any question, please ask. For example, if I ask you that if, uh, for example, if there is a aldehyde CHO, and if I am putting that hydrogen, I am substituting the hydrogen with chlorine, the how C double bond O peak will change. For example, if you have a sample and it has a functional group aldehyde CHO, let's say acetaldehyde CH3CHO. Now I am changing that hydrogen with a halogen chlorine atom, that now becomes CH3COCl. Now how C double bond O peak will change? In CH3CHO, the C double bond O peak appeared, let's say 1720 centimeter inverse. Now I am substituting the hydrogen with the chlorine. Now what will be the peak position? Yes. No, no. Here it is not energy gap. Don't make confuse because it is not electronic transition. Electronic transition happens in UV phase, but here that is bond vibration. Now you should look at the bond energy or bond vibration, how it can change. Whether bond strength is reducing or it is increasing. Yes. Hmm. No, mass number. How? No, no. I'm only talking about C double bond. This C double. Let's say this C double bond. Now that oxygen, I am not substituting oxygen. What I am substituting, that because carbon has four valency. Okay. Now one is CH3 and another is hydrogen. Okay. CH3CHO. Now I am substituting that one hydrogen with a chlorine. So what will be the effect on this particular C double bond one? Then you can answer it. You are going in the right direction. Just chlorine has minus I effect. Now I am asking you that if Cl has minus I, how it will impact this C double bond? Because obviously minus I means it will impact this C double bond. So basically what will happen? Wave number will be not increased. It will be in lower. I mean, uh, because it will come around, instead of 1720, it may come around 1660 or 1670. Now why? Because if Cl has minus I, so that means what is happening? The electron density around carbon is reducing because it is attracting. Cl is attracting electron from carbon to chlorine. Okay. Now because of that, this pi electron little bit shifted towards the C. So that's why that exactly double bond will not bonded at 2, it may be 1.8 or 1.9. So bond strength will be reduced little bit because of presence of Cl. Now when bond strength is little bit reducing, so obviously it will shifted to the right hand direction from higher wave number to lower wave number. Is it clear? Understand na? Now I another example. If I am putting that seed instead of chlorine, I am putting one CH3 group here. Ah, it will be because of plus I, so little bit it will be shifted to the left hand direction, higher number. Okay, so let's go to the question answer. So I have said few question. I think you can answer it very easily. So first one is, which one of the following statement is or are true? So first is, homonuclear compounds don't absorb IR radiation. Whether is it right or wrong? It is true or wrong? Homonuclear compound don't absorb IR radiation. Why it don't absorb? Exactly, absolutely right. The next is, twisting and wagging modes are out of plane vibration. I don't know whether you have remembered or not. Yes, yes, out of plane vibration. Yes. Then dark black compound often show 0% transmittance. Ah, it is all of the above. Yes, all of the above. So that's why I have asked you that when you have some very dark color compound, you should go for the KBR mode, because from ATR there may be very less chance to get reflected light from the deep color sample. Now, what is Kubelka-Monk function? Basically, that is used for the drift mode. That is also a mathematical formula like ATR to change the spectrum. So, what actually it do? So, there are four options: convert signal into absorbance, convert signal into wave number, convert signal into frequency, convert signal into wavelength. In case of drift, actually Kubelka-Monk function is used. So, what it actually do? This mathematical conversion. Anybody know? So it actually change the absorbance. It convert the signal into absorbance, because what is diffuse reflectance infrared Fourier transform. So by after taking the data, so automatically through the software, it is already included with the software, this function. So it will change the signal into absorbance data. So then you will get the absorbance spectrum from the FTR analysis. Now, which of the following chemical is used to make pellet in FTR spectroscopy? I think you can answer this. Which one of the following chemicals is used to make pellet in FTR spectroscopy? KCl, KBr, K2O, KH. Yes, it is KBr. The next is a matching problem. So match the following IR spectroscopy: transmission, drift, ATR, reflectance. So these are the four different mode to perform FTR analysis. So what will be the answer? Transmission. Transmission is related to thin film, because only through thin film transmitted radiation can go through. We can take the transmitted radiation. Now drift is related to Kubelka-Monk theory. It is related with the drift mode. Now ATR, I have already told what will be the ATR. ATR will be which one? Anybody response please? ATR mode we have discussed. No, from no, acha, you are going, you go for the shiny sample. I mean option A. No, you should go for ATR is zinc selenide. Zinc selenide substrate is used, na? Either diamond or zinc selenide. Reflectance is shiny sample. If it is shiny sample, then you can collect the reflected radiation. So what is the answer? Transmission, option B. Acha, option C. Now transmission is thin film, 2D, 3B, C. C, right? That's what we discussed, that 3 ATR is uh, zinc selenide and reflectance is shiny sample. Okay, so
I think you have a little bit idea now about UV and FDR. But again, I am requesting all of you, if you have any doubt, you may mail me. I can, uh, I will respond obviously. And for your reference, you may read one book, that is Fundamental of Spectroscopy by Maccas and Banuel. So that is a very good book for basic. If you interested about spectroscopy, you may go through that. It will be very helpful for you. Otherwise, you may also go for YouTube. There are lots of YouTube video available right nowadays, so you can also get knowledge from there. And otherwise, the little bit I think the what are the basic principle, how you should prepare sample, and what is the importance, why I should go for this characterization. So you have now a little bit idea. So I'm stopping now for today, and we'll meet again next week. Till then, stay happy and stay well. Okay, bye bye. Thank you. Welcome.